Okay, I want to talk to you about some content that you are seeing on the homework. And this is a situation where you have a plate that has positive charges on it. Of course, it's going to be distributed throughout the plate. And you have a plate with negative charges on it. Of course, the negative charges are going to be distributed throughout the plate. And remember, the electric field is directed from the positive to the negative plate. Whoops. Like that. And the lines of equipotential, I'll draw those as well, are going to be perpendicular to the lines of the electric field, and they're going to look like this. So these are the equipotential lines. Okay, and then the blue ones are the electric field lines. And of course, outside the plate, as we talked about in class, electric field is 0 out here for reasons we discussed, that it cancels between the positive and the negative plate outside of the two plates, and it reinforces within the region between these two plates. Now we're interested in this because this is the device that we call a capacitor. I'm going to show you by Tuesday what the characteristics are of this plate that make it useful to us to think about. And what's interesting is if we can determine if we know what the potential difference is between these plates, if we know, let's say this one's 0 here, potential of 0, and this one is a potential of 10 volts, 100 volts, or something like that, and we know the spacing between these plates, we can determine the strength of the electric field between these plates. And once we know that, we can back out and determine the charge that's on each of these plates. And that's what the homework addresses. And you're going to have the same size positive charge as you have negative charge on these plates. But I thought I'd give you an example of how this could work. I'll go the other direction. I'm going to just start by saying, let's say we have a charge of 1 plus 1 microcoulomb per square meter on that plate, and negative 1 microcoulomb per square meter on the plate on the right. So from that, let's determine what the electric field strength is in the region between the plates. And so we know for a single plate that the electric field is going to be equal to the value, or the magnitude of it is going to be equal to sigma over 2 epsilon 0. That's what we came up with in class the other day. But for a double plate, where they're opposite sign on each one, or opposite charge, we can say that the electric field between the plates is equal to sigma over epsilon 0. That's twice what it was here. 2 times the single plate's electric field exists between the plates of opposite charges. All right, so we can figure out what that electric field strength is going to be. That electric field strength is going to be equal to 1 times 10 to the minus 6 divided by 8.85 times 10 to the minus 12. And the units, again, are newtons per coulomb, or, it turns out, and I'll talk about this later, volts per meter. Either one of those are identical. So if we do the math, we talked about this last time, I think it comes out to be 1.13 times 10 to the 5th newtons per coulomb between the two plates. All right, so that means that this electric field here, I'll make this one red. I think I will. It's not letting me pick it, it's weird. All right, if I make this one red, like it is up here, and draw the electric field lines, like that, these electric field lines are going to correspond to that strength electric field. Now the potential, when you have, what's interesting about the potential, remember we talked about the potential for, in general, is equal to the integral of E dot dl. We talked about this a while back, and that's what gave us the potential for a point charge being equal to this equation. Because if I integrated E dl between 2 points A and B, and I think there's a negative sign in here, for a point charge we got the potential be equal to K times Q over R. That's just review. But for a plane, it's easier. For a plane of charge, like this one right here, the potential is going to be equal to, it's still same equation, E dot dl. So it's basically, you're going to take the electric field strength and multiply it times the length, and you take tiny little lengths and you multiply these two over these tiny little lengths. But for a plane, the electric field is constant. So the electric field, the electric potential for a plane really just becomes the product, if you do the math here, of E times, I'll put the distance here, d, where this is the distance d away from the plane. So the electric field is constant, it doesn't change, but the potential does change. It's going to be highest, we'll say, at the positive plate. I'll redraw my plates here. And lowest at the negative plate. So it's going to be highest here and lowest there. All right, so here it's going to be 0, and here it's going to be some positive number. And that's often given to us in a given problem. I'll say, oh, the potential of this plate is 10 volts. So we'll know what the potential difference is between the plates. And we'll know that by taking the electric field, which is this. In this case, the electric field is 1.13 times 10 to the 5th. And the negative plate is usually assigned to be 0. So depending upon how far away these plates are from each other, that affects what the potential is going to be of this positive plate. So let's just say that the plates are separated by, they're usually a small separation. I'm going to make it a really small separation, 0.1 millimeter. Maybe like, wow, that sounds really narrow. Well, for the devices we're going to be talking about, capacitors, they are very narrow, the spaces between the plates. So if this one is 0 volts, this one over here is going to be 0.1 millimeters times the electric field strength. And that's going to be what the potential is going to be for the positive plate. So potential for the positive plate is going to be equal to 0.1 millimeters is 1 times 10 to the minus 4th meters. And I'm going to multiply that by the electric field that I calculated up here, 1.13 times 10 to the 5th. Volts per meter is the unit, or newtons per coulomb. And if I multiply those two, I get 1.13 times 10 to the 1st volts, or about 11.3 volts. Okay, so this is kind of the opposite direction of what the homework problem's like. But if you have opposite charges on two plates, you have a potential difference between those plates that you can find by finding the electric field and multiplying the electric field by the distance between the plates. That's exactly what I did throughout this problem here. In the homework, you're actually going to go the opposite direction. If I'm not mistaken, you're going to have the potential difference between the plates, from which you're going to find the electric field, from which you're going to determine the charge density on each of the plates. Okay, that's it for this video.